Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. Tonight, we drift to the very edge of understanding, to a distance so small it almost defies imagination. Roughly 1.616 times 10 superscript 3 meters, the Planck length. Here, the familiar rules of physics begin to blur. As we zoom inward, the uncertainty of quantum mechanics dances with the pull of gravity, and space-time itself seems to shimmer, as if the universe were breathing quietly around you. Take a deep breath, feel the stillness of the moment, and let your curiosity awaken while your body remains calm. Tonight, we'll explore what happens when distances become meaningless, how energy can collapse tiny regions, and how atoms, light, and the cosmos all follow the same mysterious rhythm. Let yourself settle in, knowing that this quiet journey is yours alone. Imagine trying to peer ever deeper into the universe. Past atoms, past protons, even beyond quarks. What lies beyond? Physics asks this question not out of whim, but from centuries of careful study. Every advance in observing the microscopic world, from the first lenses to the largest particle colliders, has followed a single rule. To see smaller, we must use higher energies. Visible light, the rainbow we perceive with our eyes, has waves far larger than an atom. No optical microscope, however powerful, can show the innermost structure of matter. To reveal what is smaller, scientists turned to electrons, which can be accelerated to tiny wavelengths. In 1931, Ernst Ruska's electron microscope unveiled worlds beyond light. Cells, crystals, even individual molecules. Decades later, in California, high-energy electrons scattered against protons revealed quarks, hidden layers within matter itself. And yet, there is a limit. Pack more energy into a smaller region, and the stage upon which we observe, the fabric of spacetime, begins to bend. Einstein showed us that energy and mass are entwined. Too much energy in a tiny space curves spacetime, eventually forming a microscopic black hole. Light cannot escape. No instrument can see further. This is the Planck length, a boundary where space and time ripple like restless water. To reach it would require energies unimaginably beyond anything our most powerful accelerators can achieve. It is nature's safeguard, a frontier where quantum mechanics and general relativity collide, hinting at a deeper theory yet to be discovered. As we trace inward, each scale reflects echoes of the universe's birth. Nuclear realms whisper of the first seconds after the Big Bang. Quarks touch the physics of the earliest microseconds. And at the Planck length, we brush against the very instant that spacetime itself was born. Beyond this boundary, we cannot peer, but we sense the silence as both a wall and a doorway to something greater. Even light, our faithful messenger, reaches its limit here. Waves cannot reveal details smaller than themselves. Visible light cannot show the structure of atoms, but electrons, with their shorter wavelengths, can unveil these hidden worlds. Every glimpse into the microscopic reveals more about the universe's hidden order, a delicate and silent choreography of energy and matter. So, tonight, let yourself float along this quiet frontier. Feel the calm, the wonder, the gentle unfolding of mysteries just beyond reach. The universe does not shout its secrets, it whispers them softly, inviting you to listen, to imagine, and to rest, knowing that curiosity and serenity can exist together in the same peaceful moment. Tonight, we move closer to the hidden heartbeat of matter. Light, in all its beauty, has a gentle limit. Its waves are too long to reveal the tiniest structures. A visible ray of light is hundreds of nanometers across, while an atom is only about a tenth of a nanometer. Shining light on atoms is like trying to read the smallest letters of a book while tossing ripples across its pages. It washes away the fine details before you can see them. To glimpse something so small, we need waves far shorter, finer, delicate crests that dance with subtlety. One might imagine turning to higher energy light, like X-rays. Indeed, X-rays can probe the atomic scale. In 1912, Max von Laue directed X-rays at a crystal, and the scattered pattern revealed the precise, repeating lattice of atoms. A new chapter of structural physics was born. Yet, here lies a challenge. Photons with such energy do not simply observe, they can disrupt, even destroy the delicate atomic structure they touch. This is where electrons step in, not as mere particles, but as matter that behaves like a wave. Louis de Broglie suggested in 1924 that every moving particle carries a wavelength. The faster it moves, the shorter its wave becomes. A few years later, in 1927, electrons passed through a nickel crystal and produced a diffraction pattern, ripples of probability, as if matter itself had learned to imitate light. This single discovery changed everything. Accelerated electrons could gently reveal atomic structures without tearing them apart. By 1931, Ernst Ruska had built the first electron microscope, using magnetic lenses to guide streams of electrons and create magnified images of a hidden world. Suddenly, viruses, cell membranes, and molecules, all invisible to light, became visible. The universe, once opaque at small scales, began to unfold before the patient gaze of science. The secret lies in wavelength and energy. To see an atom with light requires photons carrying thousands of electron volts, enough to scatter or shatter what they touch. Electrons, moving with far less energy, have naturally tiny wavelengths, allowing delicate observation. A photon must struggle, burn hotter, risk destruction. An electron moves quietly, revealing with grace. Modern electron microscopes can resolve structures smaller than a tenth of a nanometer, enough to map single hydrogen atoms. And yet, even here, a limit whispers to us. As wavelengths shrink, energy rises. Push too far, and the fabric of spacetime itself begins to bend, echoing the frontier we glimpsed before. The electron microscope stands in that delicate middle ground, a quiet triumph, a balance of power and care, showing the hidden architecture of matter without tearing it apart. Across this continuum, from galaxies to atoms, light and electrons each have a role. Light shows the universe's outer beauty, its shapes, colors, motions. Electrons reveal the hidden scaffolding within, the blueprint of reality itself. When scientists first saw diffraction patterns of electrons, disbelief gave way to awe. Particles that seemed like tiny bullets were also waves, dancing across the atomic grid. Richard Feynman would call this the central mystery of quantum mechanics. Nature is not classical. To truly see it, we must embrace its wave-like rhythm. And so, the universe shows its secrets in its own language. Electrons, born of matter, reveal matter. Light, though majestic, cannot. But as we look deeper, another question arises. If atoms have structure, do their hearts hold secrets too? The protons and neutrons themselves, do they hide a finer world within? Tonight, we move into part 3, where the atomic nucleus may not be solid, and the quarks inside await our gentle gaze. Could a proton shatter if struck? Or would it, too, reveal a hidden skeleton, whispering the rules of creation? Now, imagine the nucleus of an atom, not as a solid, unyielding sphere, but as a hidden landscape, pulsing with energy. For decades, protons and neutrons were thought to be the final, indivisible bricks of matter. Yet, subtle hints began to emerge, whispering that these bricks might conceal something far smaller, something mysterious within. By this time, the atom itself had been laid bare, mostly empty space, with a tiny, dense nucleus at its heart, surrounded by electrons. Ernest Rutherford had revealed this in 1911, sending alpha particles through gold foil, watching most pass through and only a few ricochet. It was as if firing a cannonball at a sheet of tissue paper could somehow bounce back. Incredible! But now, scientists dare to look even deeper, asking whether the nucleus itself had layers yet unseen. The Stanford Linear Accelerator Center, SLAC, in California became the stage for this exploration. A straight, 2-mile-long tunnel, built to accelerate electrons to near light speed. Electrons were the perfect probes, point-like, with no internal structure, scattering off their targets to reveal the hidden forms within. Each electron became a delicate radar pulse into the subatomic world. The experiment was bold. Fire electrons at protons and neutrons with energies of tens of billions of electron volts, and observe their scattering. If the nucleus were solid, the electrons would deflect smoothly. But if smaller structures existed, the electrons would ricochet in sharp, irregular patterns. And indeed, in 1968, the data revealed a startling truth. The electrons did not scatter as if striking a single lump. Instead, They bounced off 3 concentrated points within each proton, quarks. Once hypothetical, now real. Murray Gell-Mann had coined their whimsical name in 1964, borrowing quark from James Joyce, a hint at something deeply fundamental. Inside protons and neutrons, quarks danced, bound by the strong nuclear force, a force that grows stronger the more you try to separate them. Attempting to pull them apart simply creates new quark pairs. Quarks remain forever confined, yet this confinement gives matter its stability, holding the universe together. Inside a proton, the world is not solid but alive, a storm of energy and virtual particles, colliding and dissolving billions of times each second. Later experiments at CERN and Fermilab revealed that quarks behave nearly freely at very short distances, a property called asymptotic freedom, only to be pulled back together by the strong force. This strange behavior is unique, unlike gravity or electromagnetism, and it ensures that matter remains enduring. The energy required to probe these depths, around 1 billion electron volts, corresponds to unimaginably tiny distances, a quadrillionth of a meter. At such scales, the line between solid and void blurs. Matter is mostly space, threaded with energy, forming the structure of everything we touch, see, and are. Yet, even quarks might not be the final layer. Could there be smaller entities lurking beneath, hidden by nature's design? Each deeper step demands energies far beyond our reach, but the quest continues. As Richard Feynman once reflected, the universe is always more complex, more surprising than imagined. With every layer we uncover, new mysteries await. And so we arrive at the frontier of modern experimentation. The Large Hadron Collider, the LHC. A colossal microscope, quietly circling beneath the Franco-Swiss border. Protons hurtle around its 27-kilometer tunnel at nearly light speed, 2 beams in opposite directions, each energized to 7 trillion electron volts. When they collide, they unleash 14 TeV, a threshold chosen to probe the Higgs field, the invisible ocean that gives mass to particles. These collisions are not destruction, they are delicate inquiries. The energy compresses into a space smaller than a nucleus, recreating the universe as it existed for 1/trillionth of a second after the Big Bang. The vacuum itself shimmers, particles flicker into existence and vanish, and energy flows into mass and back again. This is why the LHC is a microscope, not just a collider. Each increase in energy allows us to peer at smaller scales. Visible light reveals cells, electrons unveil atoms, and GUVI-level beams expose quarks. Beyond this, the next frontier beckons, probing the Higgs field, reaching deeper still into the unseen layers of reality, following the quiet rule that connects all of physics. The higher the energy, the smaller the distance we can observe. Now, imagine standing before the mightiest microscope ever built, the Large Hadron Collider. Inside its 27-kilometer ring, protons race near the speed of light, guided by 1,232 superconducting magnets chilled to just 1.9 Kelvin, colder than the void between stars. The vacuum in the beam pipe is emptier than the space that separates galaxies. Every bend, every pulse, every magnetic whisper keeps these beams aligned to within fractions of a millimeter, until they finally collide inside detectors as large as buildings. Atlas, CMS, ALICE, and LHCb. These instruments are not hammers, but ears. Atlas and CMS, the twin giants, allowed physicists to glimpse the Higgs boson in 2012. Among billions of collisions per second, only a few rare events reveal the fleeting signature of this particle, existing for less than 1/trillionth of a second before dissolving into other forms of matter. Peter Higgs himself said softly, "It is incredible that it has all come true. Not just a discovery, but proof that the Standard Model, describing all known particles and forces, is complete in one profound sense." Yet, even with this triumph, a deeper question lingers. How fine is the LHC's resolution? At 14 TeV, it can probe distances of about 1/10 of a femtometer, smaller than a proton's radius, where quarks and gluons whirl in confinement. Here, we are no longer observing particles alone, but the very fields that ripple through space. The Higgs field, the electromagnetic field, the strong and weak nuclear fields. They are not contained within space. They are space in motion. Every collision nudges these fields, revealing how they intertwine. Even with all this power, the LHC remains far from the ultimate frontier, the Planck scale. To reach it, we would need energies unimaginably higher, a collider spanning the size of a galaxy. The LHC is not the final eye, but a bridge, the sharpest tool humanity currently wields between the known and the unknown. Its collisions do more than observe, they briefly recreate reality itself, transforming pure energy into matter, if only for an instant. Each event produces jets of particles, photons, neutrinos, fragments that must be traced backward to reconstruct the moment of impact. The data are immense, distributed across hundreds of institutions in over 40 countries. Each second produces more information than an entire human lifetime of internet activity. Yet, through this meticulous global collaboration, we listen to the universe with astonishing precision, revealing its hidden patterns one collision at a time. And yet, a quiet boundary remains. There is a limit built into nature itself, gravity's subtle but unyielding hand. The closer we look, the more the universe pushes back. Every increase in energy, every attempt to see smaller structures, concentrates gravity alongside it. At first, the effect is negligible, barely a whisper. But as we venture past atoms, past nuclei, past quarks, the energy density grows to unimaginable levels. Eventually, a delicate balance emerges. The very energy used to probe a region becomes so intense that it curves spacetime, trapping light itself. The region we are trying to observe forms its own event horizon, a miniature black hole. This is gravity's quiet retaliation, the ultimate limit of observation. Compress too much energy into too small a space, and your microscope becomes a singularity. No added energy reveals smaller distances, it only enlarges the horizon of darkness. This cosmic boundary is the Planck length, about 1.616 times 10 superscript 3 meters. At this scale, the gravitational radius of the energy equals the region itself. To reach it, you would need energies a trillion times greater than what the LHC achieves. More than all the stars in the observable universe combined, focused into a single point. The universe, in its subtle wisdom, hides its deepest layers behind a curtain of gravity. The closer we attempt to see, the more it draws shut. This is not a failure of human ingenuity. It is a law of the cosmos, a fundamental property of spacetime itself. Even at the edge of our mightiest instruments, the universe reminds us that some mysteries remain sacred, that the smallest scales are protected, and that exploration is an endless, patient dance with the limits of reality. Physicists sometimes describe this tension as a quiet duel between quantum mechanics and gravity. Quantum mechanics urges you to look closer, to refine every measurement, to focus energy into smaller regions. Gravity responds with restraint. The more energy you concentrate, the more spacetime bends, until the very idea of position begins to dissolve. At first, this was a theoretical curiosity, but it has profound implications. It establishes a boundary, not just of what we can measure, but of what can exist. Physics as we know it cannot describe what lies beyond. To appreciate how small this limit is, imagine zooming in on a proton, then a trillion times further. You arrive at the Planck scale, where distances lose their usual meaning, and time and space ripple like foam. At this point, quantum uncertainty and gravity are in perfect balance, each shaping reality in ways the other cannot override. This threshold, where energy, gravity, and measurement collide, is sometimes called the black hole barrier. Any attempt to see beyond it triggers gravitational collapse. The act of observation creates the very wall it cannot cross. And this is no mere thought experiment. It mirrors black holes in space. When a massive star collapses, its mass compresses so tightly that light cannot escape. In experiments, the same principle applies, not to stars but to the particles we probe. Kip Thorne described it with quiet elegance. As you approach this gravitational boundary, the laws of physics resist ever more strongly. This is the Planck scale, not a wall, but a limit encoded in the geometry of reality. Distances, time intervals, the distinction between inside and outside, all fade away. Gravity's counteraction is protective, preventing the universe from tearing itself apart. Yet it leaves an unfinished story. What lies beyond this boundary? How can we ever glimpse the structure of spacetime itself? This is the question driving the search for a theory of quantum gravity, a framework that unites Einstein's relativity with the restless probabilities of quantum mechanics. Some imagine discrete networks of loops, the spin networks of loop quantum gravity. Others envision vibrating strings, tiny filaments whose oscillations replace the turbulence of collapsing spacetime. Until such a theory is complete, the paradox remains. The smaller we look, the more the universe shields itself. To grasp the minuteness of the Planck length, imagine this. A human hair is 1/10 of a millimeter wide. A red blood cell is 1,000 times smaller. A proton is 10 billion times smaller than that. Keep dividing that proton repeatedly, billions of times over, 30 times in a row. That is the Planck length, roughly 1.616 times 10 superscript 3 meters. Here, space is no longer a calm fabric. It churns and flickers, twisting under quantum uncertainty and gravitational tension. John Wheeler called this quantum foam. Tiny wormholes open and vanish in trillionths of a second. Energy surges and collapses, forming brief bubbles of curvature, a storm beneath the calm we perceive. The energy needed to probe this scale, Planck energy, is immense, around 10 superscript 1 GeV. The Large Hadron Collider reaches only 14 TeV, 15 orders of magnitude smaller. To reach Planck energy, an accelerator would span thousands of light years. This is not a technical limit, but a law of the universe. At these energies, gravity folds space into black holes, preventing any measurement. Nature draws a curtain, not of matter, but of meaning. Physicists debate what this curtain signifies. Some see a wall, the smallest unit of space, like pixels on a cosmic screen. Others see a threshold, a smooth transition into a realm where gravity and quantum theory converge. Either way, it whispers, you cannot go further. From the Planck length, we also define Planck time, roughly 10 seconds, the shortest instant that can be meaningfully measured. Below it, cause and effect blur, and time as we know it ceases to flow. These scales mark the earliest chapter of the universe, just after the Big Bang, when matter, energy, and spacetime were still intertwined. Forces had not separated, the Higgs field had not yet condensed. The universe, smaller than an atom, already contained the seeds of every future galaxy. The Planck scale is not merely a number. It is the edge of cosmic memory, where familiar laws break down and something deeper begins. Exploring beyond it requires new physics, string theory, loop quantum gravity, ideas that attempt to describe a spacetime no longer smooth or continuous. Here lies a frontier where the architecture of existence itself trembles, where curiosity meets the protective hand of gravity, and where the universe quietly guards its deepest secrets. String theory replaces point particles with tiny vibrating loops of energy, each about the size of the Planck length. Loop quantum gravity, by contrast, envisions space itself as built from discrete units, little quanta of area and volume woven together in a vast network. Despite their differences, both approaches converge on a striking truth. Below the Planck scale, distance itself loses meaning. You cannot speak of something being half a Planck length apart any more than you can have half a photon. It is not merely too small to measure. It is undefined. The Planck length is not a wall to climb, but a horizon that can never be crossed, a fundamental boundary between what exists and what can only be imagined. It is the smallest tick on the ruler of reality. There is a quiet irony in this. The constant that defines the Planck length, the gravitational constant GGG, is the least precisely measured of all fundamental constants. We know the speed of light and Planck's constant with exquisite accuracy, yet gravity still eludes our grasp. In a strange way, the most fundamental scale in physics rests on the one constant we understand the least. This minimal length has profound consequences. It sets a limit on how much information the universe can store in a given region. According to the holographic principle, the total information inside a volume is proportional not to its volume, but to its surface area measured in Planck units. Reality, it seems, may be pixelated at the Planck scale, each pixel carrying a single bit of information. This insight underlies modern black hole physics. Hawking discovered that black holes radiate energy at a rate dependent on Planck area, the square of the Planck length, hinting that the universe counts information in Planck-sized chunks. So, is the Planck length truly the end of reality, or just the beginning of something deeper? For now, it is the smallest scale we can define. Whether nature truly quantizes space remains one of the most profound open questions in science. Every law of physics, every observation, assumes that space and time are continuous. But if they are built from discrete Planck-sized building blocks, then our understanding of the universe is merely an approximation. Carlo Rovelli put it simply: at the Planck scale, space is not continuous. It is made of quanta. The world is woven from loops of gravity, a granular, vibrating foundation beneath the smoothness we perceive. And if the Planck length is the last wall of the visible world, what lies beyond may not be smaller. It may be entirely different. Perhaps space and time themselves are emergent phenomena, arising from something more fundamental. This brings us to the next mystery. If a minimum distance exists, does Heisenberg's uncertainty principle itself change when gravity joins the game? Part 7. Does quantum uncertainty acquire a gravitational upgrade? When every photon used to measure a point in space also bends that space, what does precision even mean? This is the heart of one of modern physics' most delicate puzzles: how quantum uncertainty evolves under the influence of gravity. Heisenberg's uncertainty principle, formulated in 1925, tells us that we can never know both the position and momentum of a particle with perfect accuracy. The more precisely we locate something, the less precisely we can know its motion. Even with infinite skill, uncertainty remains. Reality hides its coordinates behind a veil of probability. But Heisenberg's law was written for a world without gravity, where the geometry of spacetime is fixed. Introduce gravity, and the balance begins to shift. Imagine trying to locate an electron with light. Long wavelength photons blur its position, so you use shorter wavelengths, higher energies, for sharper resolution. But at some point, the photon itself becomes so energetic that its gravity matters. The photon distorts spacetime around the electron. Measurement bends the very coordinates you aim to define. Push harder, and the distortion grows. Eventually, the photon's energy density could form a miniature black hole, right where you try to measure. Instead of seeing more detail, you see nothing. This is captured by the generalized uncertainty principle, GUP. At low energies, the familiar quantum uncertainty dominates. But as energy increases and gravity becomes significant, uncertainty in position stops shrinking, reaches a minimum, and then grows again. There is a smallest measurable distance in the universe, about the Planck length, 1.616 times 10 superscript 3 meters. This arises purely from reasoning about measurement, energy, and gravity, not from experiment. The beauty of this principle is that it unites two of physics' most powerful theories without forcing them to merge. From quantum mechanics, Heisenberg gives a law about limits of precision. From gravity, Einstein shows that energy bends spacetime. The GUP is where these truths meet softly, mathematically, inevitably. Even if no machine can reach Planck energy, nature has already built its own safeguard, the fabric of spacetime itself. It will not allow information to be squeezed into a region smaller than this scale. This gravitational upgrade of Heisenberg's principle appears naturally in string theory. Strings resist compression, stretching, and vibrating rather than shrinking. Loop quantum gravity yields a similar result. Distances and areas are discrete, indivisible quanta, each roughly the size of the Planck length. The fingerprints of this principle appear subtly in black hole physics. Hawking showed that black hole temperature and entropy depend on surface area measured in Planck units. The connection between information, gravity, and quantum uncertainty suggests that the GUP is not just mathematical, it is physical. It also redefines information itself. If there is a smallest length, there is also a smallest unit of information, a quantum bit tied to that scale. Every black hole, every region of space, carries a finite number of bits proportional to its surface area. Jacob Bekenstein emphasized that the universe stores information on boundaries, not in volumes. Black holes, holography, and quantum uncertainty converge on the same principle. There is a natural limit to knowledge. Not because our tools fail, but because reality itself is built this way. Consider the strangeness of this limit. Attempt to measure a particle's position with ever higher energy light. Accuracy improves initially, but beyond a point, the photon's gravitational field bends the particle's path, introducing new uncertainty. Push further, and a gravitational horizon forms around your experiment. The act of asking the question creates a ripple so strong that space refuses to answer. Observations from NASA and ESA echo this idea on a cosmic scale. When the James Webb Space Telescope observes distant galaxies, it is not just looking at stars, it is probing the very structure of spacetime. How light stretches as the universe expands reveals the subtle geometry of reality itself. At the opposite extreme, theoretical physicists perform thought experiments, stretching the laws of measurement to their breaking points. Both cosmic exploration and quantum investigation converge on the same question. Is there a smallest pixel of space? The generalized uncertainty principle suggests there is, but not as a rigid wall. It is more like a horizon of fuzziness, where the clarity of position and momentum trade places, blending into each other. At that edge, the universe is neither continuous nor discrete, neither smooth nor rough. It is something in between. Heisenberg himself could never have imagined that his principle, discovered in electrons, would one day touch the very fabric of spacetime. As Lee Smolin once said, the quantum is not a theory of things. It's a theory of relationships. When gravity enters that network of relationships, uncertainty becomes more than a blur. It becomes the architecture of reality. But if there is a smallest measurable distance, what about the very substance of what we measure? If matter is made of waves, and space itself may be quantized, could the building blocks of reality be something more than points? Part 8. Can strings save nature's ultrazoomed image? If particles are not points, but tiny vibrating strings, what does infinite sharpness even mean? This question gave birth to one of modern physics' boldest theories, string theory. By the late 20th century, physicists had reached the limits of their equations. Quantum mechanics ruled the small, general relativity ruled the large, but at the Planck scale, both began to break down. Attempts to merge them led to infinities, numbers so large they defied existence. The problem was not in our telescopes or colliders, but in our picture of matter itself. Up to that point, elementary particles were treated as points, zero-dimensional dots with no size, no shape, just position and charge. This simplification worked beautifully for most of nature. But near the Planck length, it caused a crisis. When two-point particles collide, all energy is focused into an infinitesimal point. The mathematics explodes. Gravity becomes infinite. Physicists wondered, what if the fundamental objects are not points at all, but one-dimensional strings? Filaments about the size of the Planck length, 10 superscript 3 meters. If particles were vibrating loops rather than dots, the infinities could vanish. Energy would be distributed along the string, never collapsing to a singularity. And it worked. Replace points with strings, and the infinities disappear. Gravity emerges naturally, not as an added ingredient, but as a consequence of string motion. At ordinary energies, strings behave like particles, appearing point-like. But as energy increases, the picture changes. Strings vibrate more violently, exciting new modes. Their effective size grows. It mirrors the blurring we saw with gravity and the generalized uncertainty principle. The more you try to measure precisely, the more energy spreads the object, preserving consistency. At extreme energies, far beyond any collider we can build, a string cannot be squeezed smaller than its length. Add energy, and it stretches, vibrating into higher harmonics. Like a guitar string under tension, resolution stops improving. There is a minimum measurable distance, roughly equal to the string's length, near the Planck scale. Below that, distance loses meaning, not because space ends, but because our tools cannot define it. String theory began modestly, as a model of the strong nuclear force, describing patterns seen in particle collisions. But the math revealed something unexpected. A vibration mode behaving exactly like the graviton, the hypothetical quantum of gravity. Suddenly, string theory was no longer about a single force, it encompassed all forces: electromagnetism, the weak and strong nuclear forces, and gravity itself, unified by the geometry of vibrating strings. Each vibration corresponds to a different particle, like violin notes producing distinct sounds. Electrons, photons, Higgs bosons, they could all be harmonics of a single underlying structure. Brian Greene put it beautifully: the universe is a symphony of vibrating strings, and the laws of physics are the melodies they play. The theory demands extra dimensions, up to 10 or 11, curled so tightly we cannot perceive them. These hidden dimensions determine string vibrations, shaping which particles exist. The forms of these dimensions, known as Calabi-Yau manifolds, fold and twist beyond intuition. Each possible shape corresponds to a different universe with its own laws. Estimates suggest 10 potential shapes, a landscape beyond imagination. Yet at its core, string theory answers a simple, profound question: why can't we zoom in forever? Infinite sharpness is an illusion. The string's length defines the smallest scale. Beyond it, energy does not reveal finer detail. It excites new vibrations. The image does not sharpen, it sings. This intrinsic softness preserves reality. In point particle theories, collisions at infinite energy produce singularities, points of infinite curvature. In string theory, the finite size of strings smooths these singularities. Energy never concentrates into a point. Space-time never collapses. Gravity emerges naturally from the motion of strings. Einstein's gravity does not need to be added, it falls out of the math. Quantum mechanics and gravity coexist, not as rivals, but as aspects of the same geometry. Space, time, energy, and vibration become one language. Direct observation remains impossible. Planck scale energies are far beyond our reach. Yet indirect evidence may appear. Subtle patterns in the cosmic microwave background, or exotic particles predicted by supersymmetry, could reveal glimpses of this hidden structure. Until then, string theory stands as a masterpiece of unification. A framework where the smallest scale is not chaos, but music, where the deepest layer of the universe is not a wall, but a rhythm. As theoretical physicist Edward Witten once said, string theory is not just a theory of strings. It is a framework in which gravity and quantum mechanics are part of a larger whole. That larger whole may finally explain why spacetime does not tear when we probe too deep, why nature's tiniest details shimmer instead of shatter. But there is another possibility, one even stranger than strings vibrating in 10 dimensions. What if space itself is not continuous at all, but made of discrete quantum building blocks? Tiny chunks of area and volume, woven together by the spin of spacetime. Part 9. What if spacetime is a discrete quantum lattice? What if the smooth fabric Einstein described so beautifully is an illusion? Beneath everything we know, the universe could be woven from discrete quantum threads, a cosmic lattice, granular and finite. This is the daring premise behind one of modern physics' most fascinating theories, loop quantum gravity, LQG. Unlike string theory, which begins with vibrating energy, LQG begins with geometry itself. Where string theory treats the universe as a symphony of energy, loop quantum gravity treats it as a network of quanta of space. To understand why this matters, we revisit a problem Einstein left unresolved. His general theory of relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Planets follow curves, light bends along them, everything flows smoothly. But at the smallest scales, the Planck length, about 1.6 times 10 superscript 3 meters, that smoothness crumbles. Quantum fluctuations ripple through spacetime like waves on a restless sea. LQG takes this breakdown seriously. It does not unify gravity by adding particles or extra dimensions. Instead, it rewrites the very concept of space. Space is not continuous. It is quantized. Just as light comes in photons and energy in quanta, space itself comes in indivisible units, the smallest possible chunks of area and volume, each roughly the size of the Planck scale. In this picture, the geometry of spacetime is a network called a spin network. Each node represents a quantum of volume, each link a quantum of area. Together, they form the microscopic scaffolding of the universe. Viewed from afar, this network looks smooth, just as a beach appears smooth from a distance despite being made of countless grains of sand. Up close, continuity dissolves into discrete vibrating units. Space is built from loops, closed loops of gravitational field lines interweaving into a finite, interconnected fabric. Time too is quantized, advancing in tiny jumps rather than flowing continuously. Reality at its deepest level ticks like a quantum clock. Carlo Rovelli, one of the founders of LQG, explains it simply. At the Planck scale, space is not continuous. It is made of grains. The world is woven from loops of gravity. This is not poetic imagery. The theory rests on rigorous mathematics. Using Einstein's equations reformulated in quantum form, physicists found that areas and volumes can take only discrete values, much like the quantized energy levels of electrons in an atom. Even empty space is structured, a quiet web of quantum geometry forming the stage for everything that exists. Space is not nothing, it is something with its own atomic texture. At larger scales, this texture averages out, giving rise to the smooth spacetime described by general relativity. Einstein's theory is not discarded, it emerges naturally from the collective behavior of these quantum loops. In other words, the apparent smoothness of spacetime is an emergent property, like mist that, when magnified, reveals countless droplets. The implications are profound for singularities, the infinite densities predicted at the centers of black holes or the Big Bang. In classical relativity, singularities mark points where equations break down. In loop quantum gravity, the quantum structure of space prevents such infinities. Space cannot compress beyond a single quantum of volume. The Big Bang, then, may not have been a beginning from nothing, but a big bounce, a transition from a prior universe that collapsed and re-expanded. Observations from NASA's WMAP and ESA's Planck satellite map the oldest light in the universe, the cosmic microwave background, providing a picture of the cosmos 13.8 billion years ago. These match general relativity beautifully, but cannot yet probe what came before. LQG suggests a pre-existing phase governed by quantum geometry rather than classical spacetime. Every atom, planet, and galaxy would then exist suspended in a vast network of quantum threads. Gravity, time, and spatial shape all emerge from the way these loops twist and connect. It is strange, yet logical. Energy and matter are quantized, so why should space itself be any different? Experimental confirmation remains elusive. The Planck scale is far beyond telescopes or accelerators. But physicists search for indirect clues, subtle imprints in the polarization of cosmic light, tiny irregularities in gamma-ray bursts traveling billions of light-years. If spacetime is granular, photons of different energies may travel slightly differently, a fingerprint of the underlying lattice. Instruments like NASA's Fermi Gamma-Ray Space Telescope and ESA's Integral mission are scanning for such patterns. So far, spacetime appears smooth, but the hunt continues. Loop quantum gravity is a quiet counterpoint to string theory. It does not need extra dimensions or new particles. It quantizes space itself. Where strings sing, loops weave. Both whisper the same truth. At the Planck scale, empty space does not exist. There is only structure humming beneath reality's surface. This perspective transforms how we imagine the universe. The cosmos is not a smooth stage where matter performs. It is a living network, dynamic and self-interacting. Matter curves space. Space tells matter how to move. Beneath both lies a hidden architecture of loops and links. This quantum geometry could unify the two greatest theories in physics, quantum mechanics and relativity, without contradiction, a universe built not from particles in space, but from space itself becoming quantum. Lee Smolin writes, "Space is not what it appears to be. It's a network of relationships between quanta, a web that gives rise to geometry when viewed from afar." Part 10. If we go even deeper, beneath the loops, to where information itself may be the fundamental fabric of reality, what can we measure? If distance is only an approximation, what remains real? near and far, before and after, here and there. These concepts may dissolve when we look too closely. This marks the quiet edge of modern physics. After centuries of measurement, from Galileo's telescopes to the James Webb Space Telescope, we are approaching a limit not set by technology, but by nature itself. Two independent lines of reasoning converge, one from gravitational collapse, the other from quantum limits of measurement. The first path is relativistic. Einstein's theory tells us that energy curves spacetime. Concentrate too much energy in a small region, and the curvature grows so steep that light cannot escape. A horizon forms. The region becomes a black hole. This means that if we try to probe ever smaller distances with higher and higher energies, we eventually reach a threshold where the experiment itself collapses into a gravitational well. Beyond that point, nothing, not even information, can escape. The act of measuring destroys the very thing being measured. The second path comes from quantum mechanics. Heisenberg's uncertainty principle tells us that every measurement carries a built-in fuzziness. The more precisely we measure position, the less precisely we can know momentum. This is not a flaw of instruments, it is a property of the universe. But when gravity enters the equation, when the measuring photon itself carries enough energy to bend spacetime, something remarkable happens. Increasing energy to sharpen position eventually increases curvature, which blurs it. There is a balance point where further precision is impossible. This modified rule, known as the generalized uncertainty principle, tells us that below the Planck length, about 1.6 times 10 superscript 3 meters, the very concept of distance loses meaning. It is not that we lack a microscope. The universe itself no longer offers coordinates to define closer or farther. Two independent lines of reasoning, one from gravity, one from quantum theory, lead to the same boundary, the Planck scale. At that boundary, Einstein's smooth spacetime and the probabilistic world of quantum mechanics are no longer separate languages. They merge, clash, and demand a new grammar, a unified theory treating both as equals. That quest to unify gravity and quantum mechanics is the central story of modern theoretical physics. Two great paths have emerged. String theory proposes that everything, from electrons to spacetime itself, is made of tiny, vibrating filaments of energy. These strings are incredibly small, roughly the size of the Planck length. They do not allow infinite sharpness. Adding energy stretches and oscillates them, never collapsing into a singular point. Gravity arises naturally from their motion. Loop quantum gravity takes a different approach. It starts not with strings, but with space itself. Geometry is quantized, built from discrete loops and nodes called spin networks. Volumes and areas are granular, each a quantum of geometry roughly the size of the Planck scale. Though distinct, both theories point to the same profound conclusion: space and time are not fundamental. They are emergent byproducts of deeper relationships. The smooth spacetime we observe is a mirage, appearing when countless quantum interactions blend together. At macroscopic scales, galaxies, planets, oceans, atoms, this mirage works perfectly. GPS satellites depend on it, light follows it, NASA's spacecraft navigate it with astonishing accuracy. But zoom far enough down, and the coordinates guiding rockets and photons dissolve. At the Planck scale, a ruler has no meaning, time has no sequence. The universe is not here or there, but a web of interactions flickering between potential states. This strange realm may be the birthplace of everything we see. The laws shaping the first instant after the Big Bang, the inflation of space, the formation of matter, the seeds of galaxies, all tracing back to the regime where geometry itself was quantum. NASA's WMAP, ESA's Planck, and now the James Webb Space Telescope have pushed observational limits ever closer to that beginning, revealing the universe hundreds of millions of years after the Big Bang. But the true origin, the quantum moment of spacetime's birth, remains hidden behind this natural wall of uncertainty. Carl Sagan once said, "We are a way for the cosmos to know itself." Yet it seems the cosmos has drawn a boundary around its own reflection. We can observe stars and galaxies, trace spacetime curvature, but beyond a certain precision, nature refuses to be seen. This is not a dead end. It is an invitation. If distance itself is only an approximation, then physics must find a language deeper than geometry, a theory not of where things are but of how they relate. In some approaches to quantum gravity, that is exactly what happens. Space emerges from entanglement, from the way quantum information is shared between systems. The act of connection creates geometry. Distance is not a property of the universe, it is an effect of interaction. Space exists because particles exchange information. Without interaction, there is no between. At the deepest level, reality may not be made of things, but of relationships. The universe is not a place, but a process. These ideas remain untested, maps drawn at the edge of knowledge, beautiful, self-consistent, waiting for data. Great observatories like JWST, LISA, and the upcoming Einstein telescope may one day detect subtle signatures, small deviations in wave propagation across billions of light-years, revealing the fingerprints of quantum geometry beneath relativity itself. Even if that day is far away, one truth is clear: the closer we look, the less we see. Not because the universe hides its secrets, but because space, time, and measurement themselves melt under the heat of precision. At the Planck scale, distance is not wrong, it is incomplete. A language that breaks down when the conversation goes too deep. What lies beyond may not be smaller or larger, but entirely different. As theoretical physicist Nima Arkani-Hamed puts it, spacetime is doomed. Not vanishing, but a shadow, an approximation of a richer quantum foundation. After all our measurements and equations, physics returns to wonder, a universe where here and there, now and then, are not final truths, but patterns emerging from something deeper, something fundamental, something still unnamed. When we reach the limit of measurement, science does not end. It transforms, from measuring to understanding, from mapping the universe to feeling its structure unfold through logic, mathematics, and imagination. In that quiet realization, the cosmos does not shrink. It expands inward, toward the very fabric of what it means to exist. If this journey has brought you even a moment of peace, I am deeply grateful you are here. A gentle like or soft tap on subscribe is more than a gesture, it is a quiet sign these stories matter. And if you'd like, share where in the world you are listening tonight. Your presence is a small light across the dark, endless sky. Thank you for exploring with me. Until next time, rest well, and may your dreams drift gently among the stars.